Clojure is a dynamically typed functional language that runs on the JVM. Today's guest, Alex Miller, gives us an overview of Clojure's core functionality. Alex is a developer of Cognitect, and he is the founder of the Strange Loop conference as well. There's some great talks from the Strange Loop conference, if you haven't heard of Strange Loop, on YouTube, so check those out. In today's episode, we discuss the data structures, the garbage collection strategies, and the concurrency support of Clojure. How does Clojure compare to other JVM languages like Scala and Groovy? How does Clojure copy immutable data structures without copying all of the data? How does a Clojure program get evaluated and converted to Java bytecode? These questions and many others are discussed in this episode. Before we get to that episode, a few quick announcements. Software Engineering Daily community has started working on a project called Software Daily. We are building an open source news and information site about software, and we've been making significant progress. We are particularly looking for somebody who is familiar with React.js or Node.js, and particularly somebody who wants to build the server-side aspect of Software Daily. This is an open source project. There's not really any profit designs in mind, but we just want to build a really good software engineering news and information site. And you can also go to softwareengineeringdaily.com, where you can find out how to become a host for Software Engineering Daily. You can find links to the Slack channel, links to my Twitter account, my email. You can sign up for our newsletter featuring curated content that we find throughout the week. So that's it. Check out Software Daily. Check out softwareengineeringdaily.com. And with that, let's get to this episode about Clojure with Alex Miller. I had a crazy idea a couple weeks ago. It's a photo sharing app that only has pictures of cats. When I finish my photo sharing cat application, I will be deploying it to Linode, because Linode is the fastest hosted Linux provider. I don't want to get locked into a proprietary platform that's going to overcharge me as soon as my app gets popular. I just want a fast Linux server with simple pricing. Go to linode.com/sedaily and get $20 in free credit today. Plans start at $10 a month, so my free $20 will be plenty to launch my cat photo sharing app. Once I need to scale, I can use tools like node balancers and backups, and Linode has built-in dashboarding and metrics so that I can see the traffic to my Linode servers, and I can understand how many of my users are posting cat pictures and looking at each other's cat pictures. Go to linode.com/sedaily and get $20 in free credit today. The plans start at $10 a month, so it's a great deal. Thanks to Linode for sponsoring Software Engineering Daily. Now let's get on to this episode. Alex Miller is a developer at Cognitect and the founder of the Strange Loop conference. Alex, welcome to Software Engineering Daily.
Hello. Glad to be here.
I'm happy to have you. There have been actually a lot of listeners who have been asking for more episodes about Clojure, so I'm happy to have you on to talk about Clojure. And let's start by just saying, what is Clojure?
Clojure is a dynamic functional language. It runs on the JVM, and then there's also dialects, Clojure script, and Clojure CLR that run on transpile to JavaScript, and that run on the .NET virtual machine as well.
And the creator of Clojure is Rich Hickey. Why did he create Clojure initially?
I think what he wanted was something that had the small core and flexibility of Lisp that ran on a host that provided a lot of facilities. So things like garbage collection and high performance over time, and with the just-in-time compiler and things like that. That also had immutable data structures and functional programming and good support for concurrency.
Right, and it seems like some of the desires he had in creating Clojure were around his discontent as a Java developer and just object-oriented programming in general. I think he had been doing a lot of C#, a lot of Java. What was the source of the skepticism around object-oriented programming in these types of languages, Java and C#?
I think part of the problem is so some of the things that I think Clojure sort of picks and chooses which parts of OO it sort of carries on. And so the idea of polymorphism, of having sort of conditional behavior based on some aspect of your data, is a good one, and one that exists in Clojure in a couple of interesting ways. But the aspects of OO that Rich was less enthused about were encapsulation and sort of concrete inheritance. So those two things are things you will not find in Clojure.
What are the problems that those lead to?
Yeah, so with OO, the problem with OO is that it bundles things together, right? It bundles this notion of usually you're storing your data in fields, and then you're encapsulating that inside of a class and protecting it, and then providing access to that through methods or some sort of accessors. So there's a bunch of problems with that. And I'll mostly speak from like a Java perspective because I have a long Java background before I came to Clojure. So that's what I'm most familiar with. But I think most of these things also translate to some degree to other things like C++ and C# and Ruby and things like that. Though the problem with fields and this notion of fields is like in Java at least, those fields don't come with any sort of protection built in. So a lot of the encapsulation involved is basically giving you hooks to allow you to add safety around access to field data. That otherwise we would just access the fields directly, but that's not typically what's done in Java. Typically, you go through some sort of getter method, and that gives you the opportunity to make a field, synchronized or something like that. And I think the problem there is that so Clojure takes a completely opposite approach of, instead of building things around these mutable fields that can change in place, instead we build up data, and that data is immutable and sort of immutable values. So you start with immutable pieces at the bottom, things like numbers and booleans and strings. Strings aren't immutable in every language, but most modern languages, those are immutable as well, and that includes Java. And then how do you sort of start to compose those? And in Java, you use an array list or a hash map or something like that. And that, as soon as you do that, you then have this mutable object that's wrapped around your immutable values. And so in Clojure, we have persistent collections, vectors, sets, lists, and maps. And those core collections are all immutable, which means that you can treat a vector of other values as an immutable value and pass it around, and it starts life and continues its life for its entire existence as an immutable, thread-safe thing. And so you don't need to protect access to it because it is inherently safe to pass it around, and you never have to copy it or do things like that.
So you're talking now about Clojure's encouragement of immutability and immutable data structures, and this ties into the fact that Clojure is a functional programming language. Why are immutable data structures so useful for functional programming?
Well, like I said, one of the biggest benefits is that they're inherently thread safe. So that eliminates a whole class of really nasty and hard problems with sort of sharing data across threads that you have to deal with in languages that are based on sort of mutable fields and locks and things like that. So you never do any sort of locking type semantics in Clojure, really. And so you can just very safely pass around your data across threads and not care about any of that stuff. Functional programming, with respect to that, generally things are happiest in Clojure when your program is primarily immutable values, which most things are by default, and pure functions that translate from one immutable value to another immutable value. You can write very large percentage of your programs that way. And that makes them easy to test. And it makes them easy to reason about because you know that a function will always, produce the same output if given the same input. And those are both great things.
So since we aren't mutating our data structures, does that mean that we're copying them on a regular basis?
No. And so that's kind of if you go back and look at like the commit history for Clojure, you'll see that there are a couple of core areas that were the first things that Rich worked on. And one of those is the persistent collections. And the trick with persistent collections is that you want to use what's called structural sharing. So as you modify, sort of in air quotes, an immutable persistent collection, you create a new collection, but because the old one is immutable, you can share large portions of its state. And that means that you can efficiently create a new data structure because you only have to create a little bit of extra structure that reuses a lot of the old structure. And sort of the simplest way to think about this is if you think of a linked list. A linked list is a persistent data structure. It has all of these same properties. If you have an existing linked list and you want to add a new element at the beginning, you can do that. You just create a new cell and point to the old linked list. And so that allows you to share 100% of the old one and just add on a new element at the beginning.
Is this what's called path copying?
That is not. So when you look at, in particular, vectors and in Clojure, sets are really based on the map implementation. So really the two different implementations that are important are really vectors and maps. And they're both based on this sort of tree structure internally. And so the notion is that when you, for example, add an element into a vector, at the end of a vector, that you might be able to reuse most of the existing tree that's representing the old vector and then sort of add a new root on top or a new path on the side. Or if you modify an existing thing, you might be able to share subtrees on either side, but just copy the path in the middle and modify just the portions that have changed.
Okay, so if I am using these data structures in Clojure, do I need to be explicit about how I'm copying data structures, or does this typically get taken care of under the hood for me?
You don't need to care at all. So, I mean, you can just pretend that it's a collection that has functions that operate on it. And so if you have a vector, then you have functions like conj, which is short for conjoin, which just means to add a new element where it's efficient, which for vectors is at the end. Or if you've got a map, you have a function called assoc, which is short for associate. And so that associates a new key value pair into the map, and it gives you back a new map. And so all you do is just invoke a function on the map and get back a new map.
How do these aspects of Clojure data management change the garbage collection story for Clojure?
Well, it requires a garbage collector, so that's an important part because you are going to be you're creating linked structures in memory, right? And over time, people are going to stop referencing some or all of a data structure, and at that point, the GC has to notice and clean those up. Fortunately, the JVM has had probably more thousands of person years of effort put into it than any other platform on the planet, and so there's a ton of work that's gone into that to make that good and fast and tunable and work in a wide variety of conditions. Not that it's perfect, obviously, if you know anything about, if you mess with garbage collectors at all, there's all sorts of cases that don't work for you, right?
Yeah. So when you write a garbage collector for a language that's built on top of the JVM, does that mean you have to fork the garbage collector and write a new one, or how exactly does that work?
No, not at all. So, I mean, that's the big benefit of building on top of a platform with as many features and stability as the JVM, is that you get that for free. So the way that Clojure works is or the way Java works is that you take Java source code, which is compiled by the Java compiler into Java bytecode or JVM bytecode, which is then run on the Java virtual machine. So there's really two layers, the Java source, and then there's also the JVM bytecode. And so what Clojure does is it takes Clojure source code and compiles it directly to JVM bytecode. And then, so once you've done that, then you're doing exactly the same thing that the Java compiler does, and you get that for free basically. When you construct objects in the JVM, once they're no longer used, then they're available for garbage collection. So there's nothing special that needs to be done there, really.
Okay, so I want to talk a little bit more about just writing code in Clojure. One premise of Clojure is that, as you said, we can build a substantial portion of our programs simply using these simple data structures like maps and lists and vectors. And so this should be an idiomatic part of the language because it will reduce the size and complexity of our programs. How does the language encourage using these fundamental data structures rather than, I think of Java. In Java, I'm always making new data structures to do my new functionality.
Well, I mean, that's just really how all Clojure code is written. I mean, there is a Clojure sort of collection model, and I've written a lengthy post on this on my blog at insideclojure.org. I think it actually is the last thing I wrote there. So if people are looking for it, that's easy to find. But Clojure does actually have a really nice set of collection interfaces written in Java under the hood. And then the Clojure collections are implemented in terms of those interfaces, and then most things in Clojure are really written in terms of these sort of collection traits, things like whether it's sequential, whether it's reversible, whether it's sorted, that sort of thing. So it is actually possible to write your own Clojure collections and that do customized things and have them, and they're really treated as first-class collections by Clojure if you do that. And that's I'd say more of an intermediate to advanced level usage. You can certainly write many applications without ever needing to do that, but it can be a useful tool to pull out of the toolbox. As it turns out, I mean, those are really the core collections. The list, set, vector, and map really cover you to a great degree. And then Clojure does actually also have sorted sets, sorted maps, and a few other things that are used a little bit less frequently. And then there's some libraries that people use for some additional things. But really, combinations of those can really get you pretty far.
Sure. And so talking at a lower level, could you give us an overview of the Clojure type system and kind of explain what makes Clojure's type system unique?
The sort of primitives that you work with in the language are strings, obviously, and characters, booleans. Then you have the number support is pretty involved, maybe more involved than it's worth going into, but and there's sort of a complicated story there because it is built on top of Java, and the idea with Clojure is to be able to achieve Java level performance. And so the Java fixed point or fixed precision types are sort of used by default. So you're going to be leveraging Java, Java ints and longs and doubles and things like that. And so, but with that said, Clojure also prefers that you sort of blur over some of the details of those things. That you focus really on fixed precision integers, arbitrary precision integers, fixed precision floats, and arbitrary precision floats, and really treat those as sort of the four main categories. There are some extension libraries that give you a more in-depth numeric tower and different things like that. And then we have symbols. And so symbols are just words. Usually they look like words. And they can be pretty broad. They can be pretty broad in terms of what they include, much broader than what you'd see in like a Java method name or something like that. And symbols are really used as names. They're things that refer to other things. And so you might have something that is plus. Plus is a symbol that you would see in your code, and it refers to the plus function. Or you might see Clojure.core, that's a symbol that refers to a namespace. And so symbols are used to name things, things that you're going to look up. And then we also have keywords. Keywords start with a colon and then look like symbols otherwise. They're typically words and things like that. Keywords are a little different in that they are effectively interned. So they basically always they always evaluate to themselves. And that means that different parts of the code can use the same thing. And because they're sort of interned for performance, most equality checks really turn into identity checks. And so they're very fast for that sort of comparison. And because of that, they're usually used to define constants or standard keys in a map. If you want to represent some sort of information entity, a person or a company or whatever you have in your domain, you will typically use either a map or a record with keywords as keys. And because those are sort of standard known things that are used across the program, we use keywords for that.
Okay. I'd like to walk through the evaluation of a Clojure program. So if we start with a file that has some written Clojure code, the first step of evaluating and eventually getting that to running code is we take that file and pass it to a reader. What is the purpose of a reader?
Yeah, so the reader's job is to turn a string, which is Clojure code, or really things that look like Clojure code, into Clojure data structures. And so this is where we get into Lisp's notion of treating code as data. And so the reader's step is really involved with taking a string and turning it into Clojure data. So when you see Clojure being a Lisp, all expressions are represented with the parentheses around it. All sort of invocations are represented with parentheses, where the first element in the list is the function position. So you're going to have something that evaluates to a function there. And then subsequently, you're going to have all the arguments to that function. When you read an expression like that, so if you have parenthesis plus 1, 2, parenthesis, end parenthesis, that's going to be read as a list. And so it's going to be a list that contains a symbol, a number, and a number. So that's sort of the syntax part of it, right? At that point, nothing has been evaluated or anything like that. And then the next step is really to go through compilation. And so Clojure doesn't have an interpreter. It's all Clojure code is always compiled. And so the compiler is going to take that Clojure data structure and convert it into bytecode. And that's going to generate a class. And those classes are going to be loaded dynamically in the JVM's class loader. And then they're going to be invoked. And I'm skirting over lots of details about what exactly happens, but that's the general process.
Yeah. So when you get to the bytecode format, so is there a Clojure bytecode format, or is it just Java bytecode?
It's just the JVM bytecode.
Okay, got it.
And then the other really important step that we left out there is macro expansion. And so one of the big features of Lisp has always been macros. And Clojure has macros as well. And the idea with macros is that when you treat your code as data, you can apply all of the transformation functions you already have in the language to transform the input code into some different output code. And so after a thing has been read, at the point when we go to evaluate it, at that point, if we discover that the thing in function position is a macro, instead of compiling it, we can actually go off and run the macro first. And so when you invoke a macro, you give it literal code as data. So you give it a list containing a function or a symbol representing a function and the arguments to it. And then there's a bunch of facilities for, concisely stating how we should transform that code into some other code. And you can then return that to the compiler. So you can think of macros as sort of a user-provided compiler plugin. Every macro is a little doing the job of a compiler, really, in terms of taking code and transforming it into other code. And that's what gives Lisp and Clojure this sort of dynamic and feel and the flexibility. And that's what, when people talk about the power of Lisp and things like that, this is one aspect of it.
Right. And you've said this a couple of times that in Lisp and adopted by Clojure, there's the ethos of code is data. What does that mean? What does it mean that code is data?
Well, it's exactly what I mean. What I just said in terms of macro expansion is that I can treat my code that I write. The initial code that I write might not actually. It's often not going to be the actual code that's compiled by the compiler. And so that allows me to do sort of meta programming, right? I can write my own control structure that says, like, if I want if to work differently than it normally does, I can write my own control structure, and the macro can translate that into an if or whatever else, whatever sort of larger structure I want it to, I actually want it to happen. Which means that source code that you're reading is not technically Clojure, right? It's things that are it's things that are in Clojure form, and they could theoretically be Clojure, but they don't have to be evaluatable in the form that they're stored in the source file. You can take that and you might have one short expression that expands into something that defines many vars instead, many functions based on that. So you can create say, I want to be able to create a software component or something like that. I'll create my own syntax for it, which is in parentheses and it looks like code. But all of the things inside of it can have any structure at once inside of it. And then a macro can turn that into whatever, simple or complex structure that it wants to when macro expansion is run. So it gives you this ability to program up to the problem, kind of, is the idea.
Sure, like domain-specific language composition, sounds like.
And one of the key differences, actually, with Lisp is that, so Lisp has the ability to create what are called reader macros. So you can sort of extend what kinds of things can be read by the reader. You can sort of plug into the reader itself. And Clojure very intentionally doesn't have that. Because one of the problems you can get into is that someone else might not be able to read your code because they don't have your special reader plugin. And so Clojure, Rich made a decision a long time ago that he didn't want that to happen. So we don't have reader macros. We do have some other things that cover some of the same use cases, though.
Wealthfront is an automated investing service that saves you time. As an engineer, your time is valuable. If you want to invest, but you don't want to spend significant time evaluating your portfolio and allocating assets, take a look at Wealthfront. Go to wealthfront.com/sedaily to open an account today and get a special offer for Software Engineering Daily listeners. $15,000 managed for free when you open your account. With traditional investment services, there are many humans in the loop that are doing things that Wealthfront automates away. When you pay the commissions and account fees of these traditional investment services, you're paying for work that could be done by a computer. So don't pay commissions and account fees. Maximize your gains with Wealthfront's set it and forget it investment automation. Check out wealthfront.com/sedaily. It would support Software Engineering Daily, and it would introduce you to the world of automated investing. Wealthfront.com/sedaily. Thanks to Wealthfront for being a continued sponsor of the show. Now let's get on with the show. Okay, let's shift gears completely and talk about concurrency. So before we get into how Clojure handles concurrency specifically, why don't you give us an overview? What are the typical challenges that we deal with concurrent programming that can set us up for a conversation of how Clojure solves those problems?
Yeah, I mean, I break concurrency, as far as we see it in most modern programs, into a few different kinds of problems. One is sort of like being able to push something into a background thread. Like, I want to do this thing, but I don't actually need the result for it right now. And so I just want that, I'm going to go call an external web service, and at some point later, I'm going to need the answer, but I don't need it right now. And so I want to do this sort of non-blocking background work. So that's one kind of a task. Another is I want to take sort of a stream of work items, and I want to have all my cores work on processing those items. And so I call that queues and workers, and things like that. Or in Java, executors are sort of designed for this problem. So that's it. And then another kind of problem is sort of fine-grained data parallelism. Anything that is commonly described like as embarrassingly parallel. Like I want to execute a function for every pixel on the screen, that sort of thing. Or like generating Mandelbrot images or whatever. And so that's a similar problem in some ways to the workers and queues, but having a single queue has scalability issues in terms of wanting to do all those things that don't actually depend on each other at the same, if when you're computing a different function for everything on a screen, you don't need to go through a single queue to do that. You really want some more efficient way to manage all of that parallel work. And so they tend to have a different shape to the solution.
How does Java tend to deal with these concurrency problems, and what kinds of problems does Java's approach create?
Well, Java has a excellent set of tools for dealing with concurrency. So I have no knocks against Java in this regard, and I've done a lot of Java concurrency programming, and it has an amazing set of tools, and the people that are involved with that, Doug Lee and Brian Getz and all those guys are doing phenomenal work. And so I don't want to say anything negative about any of that stuff. But they have tools for concurrent data structures, so things like concurrent hash map, and that's a great building tool. It's something we use inside Clojure and the implementation of Clojure. They have the ability to create threads and to do things like wait for threads and coordinate across threads. Again, that's all really useful stuff and things that you can use directly from Clojure.
Okay, I guess maybe the less contentious version of the question is how does Clojure manage concurrency, and why does that fundamentally contrast with how Java manages concurrency?
I think actually Clojure doesn't contrast a lot with Java in terms of how it manages concurrency. I think it contrasts a lot in terms of how it deals with state. And so I'll reframe your question in that way.
Yeah, please do.
So we talked a little bit about state and things like that earlier, but Clojure takes this fundamentally different approach to state in general. In Java, you typically are working from mutable objects that hold your state. And they have all these problems around locking and shared access to those things. And so the first level of it is, and Brian Getz, who's the Java language architect, has famously said that a lot of the problems with concurrency boil down to shared mutable state. And the solution to that is to not share or not mutate. So in terms of not mutating, using Clojure's immutable data solves one chunk of the problem. Like there's a whole bunch of common problems that are just solved by just using immutable values to start with. But you do really need to share state. Like most programs have some state that needs to be shared across the lifetime of the program that you're going to maintain and update. And multiple people need to have references so that they can see the current value of that thing. And just passing an immutable value around is not sufficient for that. You need to have independent entities that can coordinate over some shared piece of state. And so Clojure has a series of reference entities reference types that are used to provide that. And all of those share certain things, which is all of them can be read at any time without blocking. And so that means that reads are always free or almost free. If they're uncontended reads in the JVM, then they probably are they're very cheap probably. All of those things take an approach where identity is separate from state. So the thing that you share is really an identity. And if you want the state at that identity, you will go ask it and say, I want the current value of your state. And that when you want to update it, you pass something, not a new value, but a function that will produce a new value based on the old value. And The key difference there is that if two different threads send a function at the same time, they're going to be applied in one order or the other. And with concurrency, you don't know which is going to happen. But because you're applying a pure function to an immutable value to produce a new value, you're never going to produce an invalid value in there. There is just a series of points that are new immutable values, and there's a pure function that's being applied to take you from immutable value to immutable value. So you can never see bad state or partially defined state or anything like that. That's just sort of not available.
And these types of mutable reference types are vars, refs, and agents. Could you explain what these three different types do?
Yeah, you actually left out probably the most important one, which is atoms.
Oh,
But those four are generally what we call the reference types. And I'm going to start with atom actually because it's the most commonly used for this kind of problem. And so an atom is, if you're familiar with Java, it's exactly the same thing as one of the atomic types in Java util concurrent atomic. So it's something like an atomic integer or atomic reference value or one of those kind of things. It holds a single value, and you have the ability to update that value. And the way that it's done in Clojure is we're gonna create an atom, and then you're gonna call it with a function that can update it to a new version of the atom. And it really does this through basically a spin lock. And so if it's uncontended, you're going to immediately succeed and set a new value. If it is contended, then you're going to get in line behind whatever other functions are out there. And you'll just keep trying to modify the value over and over again. It turns out this all through the JVM and all of the great engineering below that, this turns out to be a really fast operation and getting faster over time as well. And so that's actually the primary means. It has turned out to be the primary way that Clojure programmers share state is to typically have some sort of a compound value, usually a map, that holds the state of our application. And then you pass a function to it that says modify that state and give me a new version of my state. And that becomes easy to test because you just got an immutable value. You apply a pure function to it, you get a new immutable value. So that's a beautiful thing to test, and it's easy to reason about and understand.
Certainly.
The problem with it is that you can't coordinate two of them. So there's no safe way to coordinate two of them together. And that's where once you need to do that, you're going to have to introduce what are known as refs. And so refs allow you to coordinate a global timeline across stateful entities. And that's done through a software transactional memory system. And this has long been, it was like one of the sort of calling cards for Clojure in the early days. And it works great. But interestingly, it's surprising how much you can get done with atoms. And so I think for me, one of the big lessons over time has been that atoms actually get you what you need 90% of the time. And then you reach for refs and the STM, maybe 10% of the time. And the way that refs work is you define a transactional boundary and you define the actions that should happen against refs in that transactional boundary. And then the STM is responsible for applying that transaction. And because you're working purely with immutable values, and that's sort of this immutable value stuff is it's a really important assumption for so many parts of Clojure. You can sort of speculatively apply functions to those refs and know that at the end of it, if somebody else happened to modify one of those refs in the meantime, I can just throw away my changes because the data is immutable. So the original values still exist. I still kept a handle to them, and I can just throw away my sort of speculative changes and fall back to the original ones and then retry my transaction. So it sort of makes that sort of transaction recovery a lot easier.
Awesome. Okay. So let's talk about other JVM functional languages. So there are these other languages like Scala and Groovy that have been built on the JVM. Why would I choose Clojure over the other dynamic JVM languages?
So I'd say Scala is not a dynamic JVM language, but it's another JVM language. And so
Oh, that's
all
right.
of those
Okay.
are,
I should have just said functional languages.
yeah. So I've done work in Groovy and Scala in the past, and I have nothing bad to say about them. All these languages are doing interesting things and making different choices in terms of how they provide things to users. And for me, what drew me into Clojure was really the fact that everything in Clojure is really designed around creating tools for simpler code. Like from having, I've been doing programming for about 20 years professionally. And when I found Clojure, I was at a point where I was really kind of fed up with it. I had just done so much programming and I was so tired of fighting just sort of the incidental complexity of everything around sort of modern OO programming that I was about ready to just give up and change careers or something, or become a manager or do something else. And so really, so many of the choices in Clojure are about avoiding things that sort of cause incidental complexity and entanglement between parts of features of the program and things like that. And I think that it's really continuing to find new ways to do that. And like the big new feature that we've been working on this year is called Clojure Spec, which is this tool for specifying the structure of data and functions. And that's really, it's a different direction than types. And it's a different way to provide some of the things that people want from types, but we believe in a way that makes different trade-offs that are more important for most programmers.
Could you talk about that in more detail, Clojure Spec?
Yeah, so this is the big thing that we've been working on, and it really lets you sort of, there's a bunch of key sort of premises baked into it. I could probably do a whole show just talking about Clojure Spec, but the idea is that you want to build up a specification for your data, and you want to, at the bottom, base that on predicates. So we don't want to build a new language that describes types or a custom vocabulary for those. We want to use existing functions, predicates in our language. So either things that are built into the Clojure core or functions that you already have lying around that might tell you that, is this account overdrawn? Like that might be a function. And you can build a spec that describes your data based on that. So that's sort of the base. And then it has the ability to a number of ways to combine predicative specs and compose them into larger and more sort of compound specs in different ways. And then you get a bunch of things for free when you do that. So you get those sorts of things get automatically attached to documentation, both sort of in your runtime environment and also in sort of whatever the documentation you generate. You get the ability. All of the specs actually are designed to act as generators, so they can produce example data that is conformant to the spec. And so you can generate examples. If you spec a function, you can not only generate examples, you can run a function called check that will generate things, basically examples that are valid arguments based on your specs, invoke your function. You have then a spec for your return type, and it will verify that your return type, the return that comes out of your function, is valid. And then there's another spec called we call the FN spec or the fun spec, which actually allows you to relate the incoming arguments to the return value. And so you can write very expressive specs that, like, for example, if you have an index of function that takes a string and a search string, and it's going to return like the index that it matched on or something like that, you can write a function spec that says so the arg spec might say I'm taking a string and a string. The return spec might say I'm getting back an integer. And the fun spec might say I want to verify that my integer is in the range between 0 and the count of the incoming source string. And that's something that's much more expressive than you can say in most type systems. There are some, languages like Idris and other things that are trying to get this level of expressivity in type systems. And you're doing all that just with normal Clojure code. So it's all sort of in the same language that you're writing the rest of your program in.
Certainly. So let's talk some about the interoperability story. So if I'm an engineer at a Java shop, all the code at my company is written in Java, and I want to start writing some Clojure code. Is there any diplomacy that I'm going to need to do with the rest of the team, or to what degree is my Clojure code going to be interoperable with other people's code?
That's a good question. So there's really two sort of directions there in terms of using Java stuff from Clojure or using Clojure stuff from Java, right? And so from the first perspective, if you're like writing new Clojure code that you want to use existing part of your existing Java base, that's generally really, really easy. Most people find that it's actually easier to call Java APIs in Clojure than it is to call it in Java. So the interop is really nice, and you can do it at the REPL, so you can do it sort of dynamically be sort of interacting with the Java API or whatever at the REPL as you develop, and that's a joyful thing compared to testing and debugging most Java programs, from my experience. And you have access to every Java library out there, so it's a huge set of libraries, obviously. Most things work really, really well in terms of how they look and how you interact with them in Clojure. There are certain restrictions because Java libraries, are going to create mutable objects and things like that. So you have to be aware about those places where things assume immutability in Java. In Clojure, but you're using something mutable from Java. There are some things like that you have to be aware of. But in general, it's a pretty nice and joyful thing to access Java from Clojure. Coming from the other direction, it really depends a little bit. There's a bunch of different techniques you can use. There is a Java API for Clojure that lets you get access to vars, which hold functions in Clojure, and invoke them and load code and do things like that. And so there is that API. What I've found the best is to define an interface that sort of separates the Clojure part of the code, and define that in Java, and write your normal interface, write your doc strings, generate your docs from it, do all that stuff, and then have your Clojure code basically implement that interface or interfaces, and just sort of provide an implementation to an API. And I found that works really, really well. In a lot of today's infrastructure, people are building microservice architectures and apps and things like that, and we see lots and lots of people who are in companies where they have some sort of microservice architecture, and they have services in many languages, and they interoperate basically by how they put messages on a bus or whatever, and so you're not actually calling directly into other languages.
Right. You have some kind of message passing layer, and you're just sending JSON between different services so that it's like language independent. So what about like mental leaps? Are there any mental leaps that a traditional Java programmer would need to make in order to be effective in Clojure?
I think like one of the things that people expect to be hard is the immutable collection aspect. In practice, I find that is almost never a problem. Like it's just really, it really is just not an issue for most people. I think definitely some people are turned off by the parens and the way Clojure looks. Most programmers that work in Clojure find that they stop really seeing them or caring about them after a few weeks or a month. And so if that feels unusual, they get over that pretty rapidly. That's not true for everybody. Some people, it is a hurdle. And I think laziness is one aspect. So we haven't really talked about Clojure sequences, but Clojure has a sort of unifying model for accessing data structures called sequences. Sequences are really sort of a logical list abstraction, basically being able to treat any data structure as if it were a logical list and sort of traverse sequentially through the list. One of the cool things about sequences is that they're also immutable and can be passed around in a thread-safe way. And you can kind of blur the line between collections and sequences pretty seamlessly. But they're also lazy, or can be lazy. And so you see a lot of times that it's a common hurdle to do something write a program that is so lazy that it doesn't actually do anything. So you forget to actually realize a lazy sequence at the end or whatever that actually is required to produce all the data. And so that kind of thing comes up sometimes in the first 6 months, for sure.
So I had a listener ask, why does there seem to be a lack of design patterns in Clojure versus a language like Java? And I want to say upfront, I don't. This is not a value judgment on Clojure. I don't think design patterns are necessarily a good or a bad thing, but this listener seems to think that there is a lack of design patterns in Clojure.
Well, I think there's two ways to take that. And so I think there's a sort of a glib way to say, oh, those design patterns are papering over flaws in the language. And so Clojure is just better that way and whatever. I don't think that's, I think there's maybe some small truth there, but I do think there are some design patterns that are working around inflexibility of different calling patterns and things like that in Java. But really, I think along that lines, functions really get you out of so many jams. It's the sort of ultimate abstraction that if you want some variable behavior, you just pass a function in, and you can choose to pass different behavior later on. And so it's not that I think that things like the Gang of Four design patterns do describe problems that we run into in real code, and that's true of regardless of language. It's just that in OO, they've design patterns sort of fill this sort of. They're going to show you a structure that's a bigger structure that's used to sort of satisfy that pattern. And in general, in functional programming, I think most of those needs are actually handled pretty amply by functions. But it's actually kind of interesting. I think another way you could look at this question is, are there other problems that show up in functional programming that have their own sort of design pattern feel to them? And I think that's definitely true. I think there are sort of application structural problems that have common solutions across different FP code bases and things like that. So I don't think it's and I think that we functional programmers, we have not done a great job of sort of cataloging or talking about those. There are some talks out there, in particular by Stuart Sierra, where he looks at different design patterns in Clojure. So I would recommend those.
You recently wrote a book called Clojure Applied. Could you talk briefly about the goals of the book and what maybe what we have not covered in this conversation that you cover in the book?
Yeah, I wrote that with Ben Van Grift, and so that was a 50-50 effort. So I want to make sure to mention him on that too. It wasn't just my book. So our goal with that really was that when you look around the Clojure sort of learning landscape, there are now, I think, really fantastic getting started with Clojure materials available, both in book form and on online tutorial form and all those kinds of things. So, and exercises, like all those things exist. And I have good answers for, if someone asks me about any of those things, I have good answers for pointing them in different directions. Similarly, there are some smaller number, but excellent sort of more advanced or comprehensive resources, things like The Joy of Clojure. But what we felt was really missing, that we were trying to plug, was really a programmer who's worked in Clojure for 3 months or 6 months or something like that. They understand the language, they understand the syntax, but they're having trouble actually structuring real applications. And so that was the gap that we wanted to sort of fit into. How can we start and assume you know the syntax pretty much in some of the core library, but you're not sure how to best use it and how to structure your applications?
Hence the name.
Exactly, Clojure applied.
Right. So let's talk a little bit about Strange Loop, which is a conference that you are the founder of. What are the goals of Strange Loop? Like, how does Strange Loop differ from other software conferences? Because just in my personal experience, I watch a lot of the Strange Loop videos, and they're very entertaining, and they are somewhat different than other conferences. But I can't exactly put my finger on what makes them different.
Yeah, so Strange Loop is a conference I started in 2009, and it's in St. Louis, which is where I live. And my idea for it was really that I wanted to, like, in retrospect, if I had not come on the name that I did, Strange Loop, which I'm really happy with and and I'm going to keep, but if I had not come up on that, like another really good name would be something like Boundaries or Edges or something like that, because I really wanted to explore places where, or create a place where people from different computing environments could sort of overlap. And like the sort of notion of like where interesting things happen in the environment is at the edges of ecosystems, where things overlap. That's where you get speciation and all sorts of hybridization and things like that. And so that was what I was always interested in, sort of fermenting, if I can use that word.
No, I think that's totally descriptive of what I couldn't put my finger on. And I think a lot of the conversations end up being about distributed systems. And I find that distributed systems is so interesting because it's a topic that's being tackled in every domain from front end to back end, and in all these different ways that do have interesting parallels. Like you look at how React.js handles something, and it tends to look somewhat similar to maybe how Kafka handles something. And I find that distributed systems is maybe the thing that is tying these things together.
Yep. Yeah, it's funny. Like last year's was definitely heavy on this distributed systems, and to some degree, like it's funny how like every year I find there are, I walk out of the conference at the end feeling like there was some sort of theme that I kept hearing about all through the conference, and I'm the sort of the lead person choosing the talks and putting together a program. And I don't know what that theme is before I get to the conference. Even though I know what all the speakers are and all the talks are, it's not obvious to me what that theme always is. And so it's really interesting to me how it becomes sort of emergent. There's sort of this, like there'll be a topic that's going on and it sort of infects all the talks or many of the talks. And that sometimes it's explicit, sometimes it's just this sort of background fuzz of what's going on right now. And so like some years it's been some really about functional programming or about static versus dynamic types or NoSQL or whatever. So it's kind of changed over the years. So that was definitely the distributed system area was there were a lot of tire fire pictures last year. So
Okay. Well, Alex, this has been a great conversation. I'm really happy you came on to have a conversation about Clojure.
Yeah, my pleasure.
Thanks to Symfano for sponsoring Software Engineering Daily. Symfano is a custom engineering shop where senior engineers tackle big tech challenges while learning from each other. Check it out at symfano.com/sedaily. That's SYMPHONO.com/sedaily. Thanks again, Symfano.
Wow.